Good morning. Welcome to the Lionhearted Academy. This is Richard Tai. We are on our 55th lesson, lesson 55 of Trigonometry series. And for the last few lessons, we have been talking about vectors. Today, we're going to go on to talk about another operation of vectors. Okay, besides vector addition, vector subtraction, addition, subtraction basically are the same. And then besides scalar multiplication, we have another vector operations in the two-dimensional plane that we can do. Is called dot product. Now, what exactly is dot product? Well, let's go ahead and talk about this, and let's see if we can figure out what is dot product. Okay, I'm going to show you how to do it, and then let's see if we can make sense of it. So, V is equal to V1 V2 components. Okay, the V1 and V2 are the X component. V1 is the X component, V2 is the X component. So we can write it separate ways. Sometimes we write V1I, remember this, plus V2J. Okay, so we can break down in component forms using the I vector and J vector as well. Alright, so U is U1, okay, and U2. So U1 is the X component for vector U, and U2 is the U component, the Y component for vector U. So you can write it like this: U1I plus U2J. So okay, those are from previous lessons. We already know that. Okay. So what does it mean to do a dot product? Using rectangular forms, using component forms, dot product, U dot. Now pay attention, this is a dot, this is not a multiplication, so it's that's why it's a bigger dot. Okay, so U dot V, what does it mean to do U dot V? It's simply U1 times V1 plus U2 times V2. So dot product is basically is the scalar. The answer, you can pay attention here, the answer is not going to be a vector product. The answer is not going to be a vector. The answer is going to be a scalar, and it's going to be the sum of the product of the X components plus and the Y components. Okay, U1 times V1 plus U2 times V2. Alright, so let's go ahead and take a look at graphically and see what it could mean here. So graphically, if I have a vector V, okay, and let's say I have a vector U, alright, go ahead and use a different color here, vector V and vector U, alright. So let's say this is my vector V, and let's say this is my vector U. So when we do the dot product, what happens is that we actually break them down into different components. They're X and Y components. So we're breaking down the components, the Vx components, the Ux components, and then Vy components. Okay. So this is Vx. I'm sorry. Alright, so this is Vx, okay, Vy, I'm sorry, Vy, and the green, I'm trying to make sure our color stays the same. This is Vx, okay. So we have V has two components, and so does U. Alright, let's see if I can try to use a different color for U. So the Ux part is down here, and the Uy part is up there, okay. So this is my Ux, which is goes in the opposite direction, and then my Uy, I'm going to use a different color here. It's kind of hard to see. It's my Uy. All right. So what does the dot product actually do? Well, you can see we multiply the two components together, okay, and we multiply the X components of U and V together, and we add out to the multiplication of the the Y components together. So what happens is, this is actually doing magnitudes. The dot product will give us an understanding of how the two vectors work together. How do they work together? If you're pulling completely in the opposite direction, or if you're pulling completely in a 90-degree angle, then you're not really working together. So, but the one direction you will be, the other direction you will not. Okay, the dot product will be equal to 0. So another way to express dot product, okay, is to use the magnitude of u times the magnitude of v, okay, times cosine of the angle theta. Theta being the angle between angle u and v. Okay, so this is angle theta. So the magnitude of v times magnitude of u and times cosine angle theta. Now, so the dot product of two vectors that form a 90-degree angle, which are called orthogonal, will always be equal to 0. So when they work together, but if the angle is equal to 0 degree, that means you're pulling them in the both vectors are working in the same direction. The forces, their magnitude multiply together, basically multiply u times v times 1. Okay, and if the cosine angle, if they are pulling in the opposite direction, okay, so let me give you an illustration here. So by looking at this formula, we can understand what does dot product really mean here. So let's say if vector u, okay, so let's let me go ahead and use a better illustration. Okay, so let's take a look at this. So if I have, I like to show you this just very simply. Okay, so if vector u is like this, okay, and vector v is like this, okay, okay, all right. So let's say this is vector v, this is vector u. They're pointing in the same direction, right? They're pointing in the same direction. So what is the angle in between the two angles, between the two vectors? Well, it's equal to 0 degree. Now, what does that mean? That means they are pulling in the same direction. That means their values, their magnitude, their forces, if you imagine them to be forces or velocities, they're working together, right? They're working together. So you need to multiply them together so that the net effect of those two vectors, the net effect of the forces are positive. Basically, you multiply them together because they're working with each other, okay? Okay, the u and v, they're working together again with each other. Now, what if v goes like this, but u goes like this? What if they form a 90-degree angle? No. Okay, what if they form a 90-degree angle? Okay, so let's say this is vector v, and let's say this is vector u. Okay, and the angle theta in between them is equal to 90 degrees. So do they contribute to each other at all? No, they don't contribute to each other at all. U and v do not contribute to either one, right? Because all the value, all the magnitude of v goes in the x direction, or all the value of the y goes in the opposite direction. They're orthogonal. When they're orthogonal, they don't have components to each other. So u and v do not contribute to one another at all. So their combined force is, there's no combined force. Does that make sense? It's like combined force. So this is at 0 degree. You can see that they combine together very well because they all pulling in the same direction. They combine exactly very well. Okay, so it's going to be a positive number. It's going to their magnitude times magnitude is going to multiply together. Here they don't combine at all, so their combined force is 0. So dot product actually is giving us an idea, a concept of combined force, how the forces combine together, how do the vector combine to in terms of their magnitude and direction. Now, what if they're pulling on the opposite direction? What if they're pulling on the opposite? What if vector v and vector u, okay, they're pulling on the opposite direction? So their angle, the angle between them, theta, will be equal to 180 degrees. Now in this case, what is cosine of theta? You see, cosine of 0 degrees is equal to 1, right? Cosine of 90 degrees is equal to 0. And what about cosine of 180 degrees? Well, it's equal to -1. So what's the net effect? What's the combined effect they're doing to each other? Well, actually it's the negative. It's going to be an opposite of their magnitude multiplied together. Okay, so that will tell us that when you're pulling away from each other, their combined force is not positive, it's actually negative. They're working against each other. So the dot product for u dot v in this case will be -1. Okay, so those are extreme cases, and most likely the cases that we will encounter will in between them. But those are very indicative of I can use these three cases to illustrate what does the dot product really mean. So again, to summarize in a short phrase, it's like the combined effect of the two forces. Okay, when you have two vectors, two forces, two velocity working on together, okay, working on some same object, what is the combined effect? What kind of scalar effect it has? What kind of magnitude? Because the effect, the answer of a dot product is a scalar. Okay, so that's what that is. All right, so now let's take a look at some details of dot product, some properties of dot product. All right, some properties of dot product. So u and v, uv and w, they are all vectors. So when we do vector u dot vector v will be equal to vector v dot vector u. So there's a commutative property. Okay, and the zero vector dot vector v will be just equal to 0. Okay, the zero scalar. And the vector product is also distributive. Okay. Vector u dot v plus w is the same as vector u dot vector v plus vector u dot vector w. Okay. All right. And what about the vector dot itself? Well, as we know, vector dot itself, this will be equal to the magnitude of v times magnitude of v times the cosine of the angle between v and itself. But the cosine angle of v between itself is just the cosine of 0 degree, which is just 1. So this is just magnitude v squared. Alright, lastly, if we have a scalar times u dot v, it would be just equal to the scalar u dot v, or you can do u dot the scalar times vector v, so it's okay. Then we can go ahead and use different ways to distribute that. Okay, not distribute, I'm sorry, it's a multiplication, because this is a scalar value too, so it's a scalar times the whole thing. Alright, now let's do a few quick examples. Okay, so let's say u is equal to 3i minus 4j, and then vector v is negative 6i minus 5j. Okay, so let's go and find out what u dot v is by using the component form. So it will be 3 times negative 6 plus negative 4 times negative 5. Alright, so it will be negative 18 plus 20, so it will be equal to 2. Alright, now the magnitude of u is 5. I think magnitude v is square root of 36 plus 25 is 51. But altogether, the dot product will be 2. So that's like, that represents the combined force, the combined magnitude of the u dot v product. Okay? Alright. Now, as we mentioned before, if u dot v, the dot product, is equal to 0, then vector u and vector v are orthogonal. Orthogonal means they form a 90-degree angle. Okay, they form a 90-degree angle, and so this orthogonal means the angle between u and v is 90 degrees. Okay, so what we can do is we can use the dot product to help us on figure out the angle between vectors. The angle between two vectors can be determined by the dot product. The angle between two vectors can be found by using a dot product. Now remember, vector u dot vector v, right, is equal to the magnitude. Alright, I draw two money slash magnitude of u times magnitude of v times cosine of the angle of theta. So to solve for cosine theta would be the magnitude of u dot magnitude of v divided by the magnitude of u times the magnitude of v And then we can use the arc cosine to help us solve for cosine theta. So let's use the example above to find the angle of theta between u and v, right? So let's go ahead and use the example above. So u dot v was -3, right? Times, 3 times -6. Yeah, it was 3 times -6 plus -4 times -5. Okay, so that's u dot v. Now the magnitude of u is 3 squared plus -4 squared square root of that times square root of v squared is -6 squared plus -5 squared. Okay. So the numerator is -18 plus 20, so it's 2. The denominator here is square root 25. Now this one is 36 plus 25. 36 plus 25, so 61. Square root 61. So altogether this is 2. 5 times square root 61. Now this is the cosine value of theta. So what do we have to do to find theta? We have to use arc cosine. Okay, so let's use arc cosine or inverse cosine of 2 divided by 5 times square root 61. And so let's go ahead and type into calculator and do the arc cosine. And so it came out to be about 87.1 degrees. Okay, 87.1 degrees. Alright, so that's one way to use the dot product to help us figure out the angles between two vectors. Alright, and we can also use the angles, we can also use the dot product to help us figure out whether they are orthogonal or not. If the dot product is equal to 0, then we know automatically they form a 90-degree angle. They're orthogonal. Alright, so today let's go ahead and stop right here. Okay, we're going to continue our discussion on vectors dot product tomorrow, or we can talk a little bit more about how to break down vectors into components, what in the projections of another vector, and also another concept called work. It's another physical concept. Alright, so if you have any questions, please leave your comments in the comment section, and we hope you join us in our next lessons. Goodbye.